Hi everyone, I'm Hongbo, a second-year PhD student from USSB PLSE Lab. Thanks for having me here. Today I will present our paper, Practical Security Analysis of Zero-Knowledge Proof Circuits. Before we get started, let me give a little background about ZKP and circuits. Zero-knowledge proofs are essential in many domains because of their ability to ensure security and privacy. It allows one party, let's say the prover, to generate a proof that allows other party, the verifier, to efficiently check the correctness of the proof without knowing any secret information. And the verifier could always detect the invalid proof. In practice, recently, ZKP technologies have been widely adopted by blockchain to allow any computation being executed off-chain. Anyone could execute the computation with ZKP, generate the proof, and submit it to the blockchain. And third party could verify the correctness of the computation on-chain efficiently, convincing themselves that the computation is valid. It's cool, but now let's still ask a question about the motivation. What can we gain via ZKP technologies? By offloading the heavy computations, such as handling millions of transactions, ZKP technologies help the blockchain become more scalable and keep the zero trust principle. A practically attractive ZKP protocol is so-called ZK-SNAC. It allows the verification process be finished without interaction between the prover and the verifier, which is extremely useful in the blockchain scenario. Now, suppose we want to construct a SNAC for arbitrary computation fx. So first, we should write the SNAC circuit to encode the f as to encode the logic of f. In that circuit, input, output, intermediate nodes are called signals. Second, the circuit is compiled into polynomial field equations semi-automatically. Finally, after the polynomial field equations is compiled, the SNAC protocol for fx is implemented for the prover and the verifier. The whole process is automatically except the compilation process. The semi-automation step is the root cause of the bug because it requests the interaction between the compiler and the developer. Now, I'll briefly explain why isn't the compilation automatic. There are two main reasons. First, some computation which is expressed as the circuit level is not expressible directly. For example, some circuits include operations which compute the score roots and that computation cannot be expressed. The developer needs to manually add constraints which specify how the output should be related to the input. In this case, the constraint might look like the output x scored should equal to the TMP. Second, even if the computation was expressible, it is highly non-trivial to automatically infer the constraint from the circuits alone by the compiler. Okay. Now let's have the significance about the correctness of the circuits. It is important that circuits and the field equations should be equivalent, let's say at least observationally, for both functionality correctness and security reasons. What I mean by observationally equivalent is that the constraint should be such that for any input x and output z, x and z should satisfy the constraint if and only if z is the output of the circuit given x as an input. If they are not, then a malicious actor can create bogus proofs that are accepted by the verifier. Unfortunately, circuits and their corresponding equations are frequently not equivalent because the developer has to write them manually. The most common type of errors we observe when constraints are not properly added are under constraint circuits. We say a circuit is under constraint if the output signals are not determined by the input signal in the circuit. As mentioned before, this allows attackers to get bogus proofs verified, as they can generate a proof saying F produce some output for a given input when F doesn't actually produce that output in the computation. Under-constraint circuits have been responsible for several vulnerabilities with a serious consequence, including drawing all tokens from a protocol or allowing double spending on the blockchain. Okay, now let me show an example making the under-constraint circuits due to the constraint computation discrepancies. The Circom code in this circuit might split into two parts. The computation part is executed by the prover, and the constraint part is executed by the verifier. The discrepancies may happen in a special case. Let's say the out 0 equals to 0, the in 1 equals to -1, and the in 0 equals to 0. So those three signals are assigned by special values. And now the constraint part will be evaluated as the right-hand side. The 0 multiples 2, constrained by 0. Out 1 multiples 0, constrained by 0. So now we discovered that in this case, any out 1 and any value of the signal out 1 could bypass the verification. The root cause is that the discrepancies of semantics between the division and multiple when the denominator is 0. To reason those bugs, let's consider how the circuit is constructed. Signals are the core symbols in the circuit. The computation part is data dependencies between signals. And the constraint part is instead equations between signals. It's hard to reason complex circuits via symbolic execution or fuzzing due to the extremely large search space, because usually the ZKP circuits will adopt extremely large number field. Thus, we extract those three core structures and abstract the original circuit into the circuit dependency graph, CDG, to describe the circuit in a more simplified but expressive way. Static analysis based on CDG allows a more scalable but still precise enough detections on vulnerabilities. As shown on the right-hand side, nodes in CDG represent signals with their symbol names, and edges in CDG represent the computation and constraint dependencies between signals. Okay, now let's review how could we detect the bug via CDG. We built the corresponding CDG of the circuits as shown in the slides. For each pair of computation and constraint edges between the same two nodes, for example, in 1 and out 0, we detect any discrepancies in the semantics of the expressions. For example, the discrepancies made by the division by 0 case, the discrepancies made by, let's say, using totally different arithmetic operators, and etc. Okay, now to detect the bugs via CDG automatically, we collected and summarized three major sources of bugs. The first one is non-deterministic signals, And the second one is unsafe component usage. And the third one is constrained computation discrepancies. Driven by these three major reasons, we designed a series of detectors working on CDG. By implementing those detectors via VDL, our vulnerability description language, our tool, DCAP, could do VDL queries on the CDG and report bugs automatically. Okay, due to the time limitation, I won't present all detail, but would like to show the key evaluation results. We have implemented 9 detectors. We collected 258 Circom circuits from 17 popular outsourced projects. We inspected results manually to distinguish actual vulnerabilities and false alarms. And our tool, DCAP, have lower FP rates. It found 81 vulnerabilities across all bug categories we mentioned in the paper. And it could identify previously unknown bugs, which were confirmed and fixed by the developers. Thanks for your listening today, and any further questions are welcome.